Hey everybody, in this AP Chem series video, we're going to take a look at the Bronsted-Lowry theory of acids and bases. First, remember in the last video we looked at the Arrhenius theory of acids and bases. Arrhenius says that acids will ionize to produce H+ ions like this hydrochloric acid shown here, while bases ionize to produce hydroxide ions like the magnesium hydroxide shown here, with the problem of not being able to explain substances like ammonia, which clearly don't contain hydroxide and yet are also clearly bases. This problem tells us we need another theory, and that's where Bronsted-Lowry comes into play. This was developed in the 1920s by Johannes Bronsted and Thomas Lowry. You can check out these two dudes in the bottom right hand corner. And what they did is just dive a little bit deeper into what's actually taking place when an acid or base gets added to water. So they said that acids are substances that don't just ionize to produce an H+. They said that these substances actually react. There's a chemical reaction taking place, and for acids that reaction involves the donation of an H+, that hydrogen ion, which is also referred to as a proton. A proton and H+ are the same thing because a hydrogen atom is only made of a proton and an electron. So if you get rid of that electron to make it an H+, all that's left behind is a proton. Let's take a look at how this works with something that we know is an acid like HNO3. The formula looks like an acid. I can see that hydrogen there. It's super reactive with metals like copper shown here. Definitely an acid, and now we can take a look at why it is an acid according to this theory. So the main way that we show this is by writing out an equation to demonstrate this proton donation. So I'm going to start by writing the formula for our proposed acid, HNO3. It is dissolved in water, so I want to mark it with that AQ. And again, there's not just an ionization of an H+, there's an actual chemical reaction taking place, and in the case of an acid being added to water, it is literally reacting with those liquid water molecules. The hydrogen from the acid, so here it's this H that I've got underlined, is going to be donated or transferred over to the other particle that it's reacting with. I often like to label that with an arrow, and then along that arrow put the H+, just to remind myself what's happening here. And that's the whole reaction. To finish the equation, we have to show what the products are. So imagine HNO3 after losing a positive hydrogen. What's left behind, of course, is NO3 that now has a -1 charge, and that charge is going to allow it to dissolve in the water. So I'm going to mark it with AQ. We also have H2O, the water molecules, that are gaining a hydrogen. So they're not going to be H2O anymore. They're going to be H3O, and that positive charge travels with the hydrogen that moved over, so it's going to be H3O+, also aqueous. So that's the completed equation, and the last thing I'll point out here is that we see the formation of a really important new ion here, H3O+. We'll eventually come to see that it's really the creation of these H3O+s that cause the solution to become acidic and lower the pH. So that's how it works for acids. Bronsted-Lowry also defines bases. They said that these are substances that react not by donating a proton, but instead by accepting a proton. Let's go back to the original particle that sort of expressed the need for this new theory in the first place, NH3. NH3 is a base, although it doesn't look like it should be. Now I can explain why by showing what happens when I add some NH3 to water. It doesn't just dissolve in the water, it chemically reacts with the H2O molecules themselves. Since the NH3 is a base, then it's gaining an H+, and it's going to gain that H+ from the particle it's reacting with, in this case, the H2O. So I'm going to draw that arrow again to show the movement of the H+ from the water to my base. To complete the chemical equation, of course, I need to write the products. If NH3 gains a hydrogen, it becomes NH4, and that positive charge goes with it, so NH4+. It's going to be dissolved in the water. My H2O no longer has two H's. It has lost an H. So we're going to write this as OH, that is now -1, and that should look familiar from Arrhenius theory. It's the presence of these hydroxide ions in the solution that's going to cause the solution to be basic or alkaline. So we have this NH3 that didn't have hydroxide ions, but by reacting with H2O, it produces them. So this is how acids and bases truly behave in terms of creating an acidic or basic solution. These definitions and equations also make up some of the key ideas for this video, so make sure to pause, take some time, and write those down. That also wraps up this video on the Bronsted-Lowry theory. Thanks a lot for watching, and here is a brief summary.